Hello everybody, this video is going to be about limiting reagent stoichiometry. This is an extension of the types of stoichiometry problems we've already been doing. We're just going to have to do a little bit of work at the beginning of the problem to help us figure out which starting value to use. So a limiting reagent stoichiometry problem is one in which you're going to run out of one of your reactants too soon. And one of them you're going to have leftovers of. One you don't have enough of, one you have extra. So the tricky part is trying to figure out, which type of stoichiometry problem is it? Is it a normal stoichiometry problem or is it a limiting reagent problem? And then the next tricky part is, if you know it's a limiting problem, then you have to figure out which chemical will you run out of first, in which you'll have extra. Once you know those answers, then you can start the problem. So let's start with figuring out how do we know if it's a regular stoichiometry problem like we've been doing, or a limiting reagent problem. And the trick here is that you have to look at how many starting values you're given. If they only tell you one number to start with, then it's a normal stoich problem. But if they give you both starting values, if they tell you how much of each chemical you have, that's a limiting stoich problem. Because now you have to figure out which one will you run out of first. You're going to be limited in how much product you can make by whichever chemical you run out of first. Okay? So here's some examples. On the left, it says if you react 25 grams of hydrogen gas with oxygen gas, how many grams of water can you make? Compare that to on the right-hand side, it says if you react 25 grams of hydrogen gas with 30 grams of oxygen gas, how many grams of water can you make? So you should notice on the left-hand side, that's one starting value. 25 grams of hydrogen gas. They're assuming that you have all the oxygen you need, that you're never going to run out, that it doesn't matter, you're limited only by how much of that hydrogen you have. Compare that to the right-hand side. You don't know if you're going to run out of hydrogen gas first or oxygen gas first. Once you run out of something, you can't keep going. You can't keep making product if you're out of one of your reactants. But you don't know if you're limited by the 25 grams of hydrogen or if you're limited by the 30 grams of oxygen. So this one on the left is a regular stoich problem, but the one on the right is a limiting problem. You are going to have to do some work to figure out which of these numbers do you start with. So a couple of words that are important to know: limiting reagent and excess reagent. The limiting reagent is what you run out of too soon. It's which you don't have enough of. The first thing you run out of. I like to abbreviate it LR. Excess reagent is whatever you have extra of. You're not going to run out of it. You're going to have leftovers by the time you're finished. I like to abbreviate it as X and then an S, excess. I like to kind of think of this as, if you ever go to the store and try to buy hot dogs and hot dog buns, the package of hot dogs and the package of hot dog buns never match up in numbers, right? You buy a pack of 12 hot dog buns, but you get a pack of 8 hot dogs. So you end up with some extra buns left over, right? That's your excess reagent. You're limited in how many hot dogs you can make by the 8 hot dog package that you have. It doesn't matter if you have extra buns. You run out of the hot dogs first, you're all finished, right? So that's a good example of this in real life, where you got to figure out what you're going to have less of, what will you run out of first. So there's typically 3 types of problems. The first type of limiting problem may just ask you to find out what the limiting reagent is. It may just only want to know what you run out of first. The second may say, okay, now that you know what the limiting reagent is, Now find out how much product you can make. So you can't do the second type of problem without also solving the first type. They stack upon each other. And then the last type of problem is once you found the limiting reagent, once you found out how much you made, now how much excess reagent do you have left over? You can't do problem type number 3 if you haven't done the first and second portions first. The thing that's tricky is that these questions are not going to always remind you that you need to do step 1 and then step 2 and then step 3. Sometimes the question, instead of having like an A, B, C portion, it's just going to say, how much excess do you have? And you have to know to do these other parts first. So that's something to make sure you're being careful of. Okay. Now, just like regular stoichiometry, this is all about mole ratios. Remember we had that silly phrase that the key to stoichiometry was mole ratios? It's the same thing here. This is all about ratios. You're still doing dimensional analysis. You're still putting units. You're still labeling things. Okay? So one of the things I like to do is I like to teach regular stoichiometry first, practice that for a couple days, then teach you that this is just an extension so that you can really see that this is the same concept, just a little bit more complicated. So when we use those mole ratios and dimensional analysis, what we're going to be doing in these limiting problems is we're going to be comparing how much we need of a certain chemical versus how much we have. The question is going to tell me how much I have, and I have to figure out how much I need. So that's what we're going to be trying to set up, is we're going to be trying to figure out a comparison here based on these mole ratios and dimensional analysis. So some very generic kind of chunked steps just to remind you of what you need to do. These are not super detailed, okay? They're just reminders. The first step is that we're going to be converting from grams to moles. Remember, the moles are what we want. We always try to get to moles. The second part is we're going to be comparing what we have versus what we need. That's going to allow us to identify what our limiting reagent is. Once we know what our limiting reagent is, then we're able to do the stoichiometry with that starting value. That limiting reagent is the one that we would start with. Now that's if the problem wants us to. Don't be on autopilot doing more work than you need to. If it only wants to know which is the limiting reagent, then stop after step 3. Don't keep going, okay? Last step would be to find your excess left over, once again, if you're asked, if it's a longer problem. So here's the first example. If you reacted 150 grams of potassium with 225 grams of bromine, how many grams of potassium bromide can be made? How much excess reagent is left? So this problem is asking us to, first we have to find the limiting reagent. I know that because I have 2 starting values. Then I need to find the amounts made. That's asking me how much of that potassium bromide can be made. And then it's asking me at the end to solve for how much excess is left over. So this is going to be a pretty long problem. It's going to have all 3 parts. Let's do the first part. Let's find our limiting reagent. Now, before we start, I will tell you there are quite a few ways to go about doing this. I personally know of about 4 different ways. I'm going to show you the way that I think is kind of the best. I think it's the best for several reasons. One, after doing this for 12, 13 years, I've noticed over the years I've taught it different ways. This way gets the fewest mistakes consistently. It seems to be hands down the safest method. The other reason I think this one is the best is because it ends up being the fastest for the most types of problems. There are some other ways of solving these that seem faster at first, but by the time you're done with an entire worksheet or an entire lab or an entire quiz, the ones that seem fast end up taking you longer in the end. So this one seems to be the fastest start to finish when you're doing a bunch of different types of problems. The other reason I like this method is it's going to be a sneak peek at a technique that we use later on in a later chapter. We're eventually going to get to a chapter called equilibrium, and we're going to learn how to make something called an ICE table. And that's just a chart. ICE is just an acronym, but we're making a chart, and we're going to put values into the chart, and we're going to use it to kind of organize what's happening. And I've noticed over the years that if I teach you how to do limiting stoichiometry with this chart I'm about to show you, the equilibrium chapter goes better and the acid-base chapter goes better at the end of the year. So to me, I think this is going to be the best one. I will give you credit on your work if you use a valid method, if and only if I can understand what you're doing, I can follow your work, you label every single thing, your units cancel properly, etc. If you have a bunch of chicken scratch all over with random things that don't cancel and units aren't on places and I don't know what you're doing, you're not getting credit for that. Even if the numbers work, you are not showing me that you understand the concepts of the unit conversion and the ratios here. So just keep that in mind. If you start going down the rabbit hole of YouTube and you start finding strange methods out there to do these problems, they're going to need to have to hold up to the scrutiny that I have for units and canceling and ratios and things like that. So keep that in mind. Okay. So back to the problem. We need to convert our grams to moles. Grams are useless, right? Grams are good for our scale in the lab, but they're not good for anything conceptually. We need to convert them to moles. So we use molar mass. We have two different substances that we need to convert. Let's start with potassium. The molar mass of potassium is 39.1. I put the grams on the bottom. The grams will cancel. I'll be left with moles. Next, the bromine. Remember that it's diatomic, so there's two of them covalently bound. So my molar mass needs to reflect that. Grams are on the bottom, moles on top. Now I have the number of moles of substances that I'm using. Remember that our ratios in our balanced equation are not gram ratios. They are mole ratios. So we need to get these into moles. Next, we're going to make our have-need chart. Okay, that's what I call it. I don't think it has an official fancy name. That's just what I call it, a have versus need chart. So we have two chemicals that we're working with. We have potassium and we have bromine. I like to just do it directly under the balanced equation. That way I don't have to label what the tops of the columns are. Otherwise, you should label the columns. I found from the earlier slide that we had 3.836 moles of potassium, 1.408 moles of bromine. Now what I'm going to do is I'm going to do a molar conversion, right? A little bit of stoichiometry. I'm going to convert from one of my starting values and figure out how much of the other I needed. You could start with potassium or you could start with bromine. It does not matter. I'm just going to start with the potassium. If I use this much potassium, how much bromine would I need to use it all up? Now it's time for my mole ratio. So there's 1 mole of bromine for every 2 moles of potassium. So if I wanted to use all of this potassium, I would need 1.918 moles of bromine. I'm going to put that in my chart, and I'm going to instantly notice a big giant problem, aren't I? I'm going to notice right away, I need 1.9 moles. I only have 1.4 moles. I'm going to run out of this, aren't I? Okay, so this is a problem. That means I can use this part of the chart to figure out that bromine is limiting. Just a little note down here, it does not matter which starting value you use first, okay? It doesn't really matter. The chart is just very valuable because we will sometimes come back and use other parts of these charts for later problems. So doesn't matter which one you start with. So now we notice we don't have enough bromine. That's our limiting reagent. We're going to run out of that first. That means potassium is our excess reagent. We're going to have extra left over. So we've now done part 1. Okay, we know that bromine was limiting. Now we're going to find out how much potassium bromide we can make. I'm going to do my stoichiometry with the limiting reagent. So that's the one I'm going to use. That's the one I care about. I'm going to go from grams to moles using molar mass. Then I'm going to use mole ratio of bromine and potassium bromide. And then I'm going to solve for grams. Couple of things here. You technically did this first step in your chart, didn't you? Right? You technically didn't need to do this part. You could have started with what you had in your have-need chart. I like to just start from scratch because if I had made any small mistake, if I had rounded too far, right, I think it's a little bit safer to just start again. Doesn't matter. You could start with your chart value. That's fine. Another thing is sometimes these problems are not going to specify what unit to solve for. Up here it says how many grams of potassium bromide can be made, which is why we went to grams. But sometimes these problems will just say how much can be made. If that's the case, then I don't care if you go to moles, right? Stop early. Don't do another conversion unless you have to. So that's just something I've noticed over the years is we don't always need to go all the way to grams. Okay. So if you would like to, you can write this part down, which is what I was talking about earlier, where we already knew how many moles we had, so I could take that and keep going. If you don't like that, if you just want to start at the beginning again, sounds good. My only caution is be a little bit careful about not rounding too early if you're going to do this, because your final answer can get off a bit. But since most of the time we don't care about sig figs, most of the time our answers are pretty obvious if it's multiple choice. Not a huge problem. Just something to be a little bit mindful of. All of the methods have a pro and a con to them. The rounding issue here is one of the potential cons of this method, but that seems to be outweighed by the pros. This, being able to get our answers correct more often, being able to do them faster, that all seems a little bit better than the rounding issue to me. All right. So now we've done the first 2 steps. Now we can find out how much excess is left. This is one of the reasons why I like these charts is people struggle a lot with the excess reagent step. I don't know why that tends to be so tough for people, but I've noticed that when we use the have-need chart, these problems where you're going all the way to the end where you're finding the excess, people do much better on. So we already found most of our chart. what we need to do is figure out, okay, I have this much of my excess reagent. How much am I actually going to need? So I'm going to take this value and I'm going to use it to solve for the missing piece. Okay, I'm going to use this much bromine. There's a 2-to-1 ratio. So that means that I am going to have to use 2.186 moles of potassium during this reaction. Now what we can do is realize I know how much I have. I know how much I'm going to need to use. I can easily do a subtraction and find out what I'm left with. Now subtract, and I find out that there's 1.02 moles of potassium left over. Once again, if you notice, the problem did not tell me I had to go to grams. It just said how much is left. So stop, be lazy, don't keep going, leave it be, okay? Just stop here and tell people you're going to have 1.02 moles of potassium left. Okay. So let's try one more. Okay. This time it says if we react 13.2 grams of iron with 6.34 grams of oxygen, how many grams of iron oxide can be made? How many grams of excess are left? First step is going to be converting to moles. So you pause the video and you try to convert both of your starting values from grams into moles. So pause and do that. All right, so 13.2 grams of iron, I use molar mass, grams goes on the bottom, 1 mole on top, and I find out I have 0.236 moles of iron. Next one, 6.34 grams of oxygen, molar mass of oxygen, grams goes on the bottom, moles go on the top. I end up with 0.198 moles of oxygen by the time we finish our conversion. Now I'm going to make my have-need chart. I'm going to be doing iron and oxygen. I just found out that I have 0.236 moles, 0.198 moles. It doesn't matter if you want to start with this one or this one. You pick. It doesn't matter. I just typically have the habit of starting on the left. So, mole ratio time. Let's pretend that I'm going to use all my iron. How much oxygen would I need if I used up all my iron? There is a 3-to-4 ratio. I would need 0.177 moles of oxygen to use up all my iron. Put that in my chart, and I should instantly notice I have more oxygen than I need to use up all this iron. So that tells me that oxygen is excess, so iron is limiting. Now I know that I need to do my stoichiometry with my iron. That's the number I'm going to do the problem with. Or you could come up here and start your stoichiometry with 13.2 grams. Doesn't matter. Now I use mole ratio to get to my product. Now I use molar mass of my product to end with how many grams I can make. So I find out with this amount of iron and this amount of oxygen, I'm going to be able to make that much product. Now, look, now it's time to find excess. And what have I already done? I've already found out how much I have. I already found out how much I need. Now it's time to just subtract. Now this time it does say grams, doesn't it? Unfortunately, we can't stop here. We have to go one step forward, one more conversion factor. Moles to grams using molar mass. I'm going to have 0.672 grams of oxygen left. Okay. So one more time, I'm just going to kind of remind you that yes, there are other things, other ways of doing this, other things you can go look up. There's so many little tricks, different methods, shortcuts. They are not all going to show that you understand the concept. So be careful, okay? You got to make sure that you're using units, that you're showing all the ratios, etc. Not all teachers use this, but you got stuck with me. Sorry, not sorry. Okay. We all do things different. We all have best intentions, right? We all think that our way is the best way. And, well, it is what it is. Okay. So I'm really going to ask you to use this chart method. Okay. All right. Now, pros and cons, right? One of the things I'd like you to make a note in your notebook about is to just be a little bit careful with rounding on this method. Yes, it's faster. Yes, it's safer. The other thing that's nice is you're more likely to get partial credit with this method. Because this method chunks things into little baby steps, it's going to allow you to get more partial credit when we're giving partial credit. Sometimes it's all or nothing, right? But another thing to maybe make a note of is this is a great way to be a little bit safe with getting some partial credit. And if you need help, you have to come see me. Please come see me first, okay? Please don't jump straight to YouTube, okay? I've seen that go bad really fast, all right? Come see me first, okay? If you're really, really struggling and I can't help you one-on-one, then I will try to show you maybe a different method and see if that clicks. If I can get an idea of what part of this is hard for you, I may be able to find a different method that addresses the piece that you're struggling with, okay? So please, please, please come see me first. We have, access period. We have class time. You can always email me for help, text message me, right? You have a teacher who is available to help you, and I want you to use me for help, okay? This is one of the harder topics we do during the school year for some people, not because it's technically hardest, but people get overwhelmed and then they shut down, okay? So don't let that happen. Come to me, we'll go over lots of practice problems. I can show you lots of tricks. I can try to figure out what part is tricky for you, right? We will find a way to make this click. Okay, but that's going to mean that you got to come see me. All right? Okay, that's it for now. Bye, everybody. Hope that was helpful.